Okay, then what happens if the light is illuminated to the solid, and what we basically want to know is that when the light is illuminated, how the energy change and how the wave function change. In this case, in many cases, perturbation theory is used. This theory is not only used for solid, but also the molecular cases. So just briefly introduce it, that if you know the ground state wave function in Hamiltonian, and then also the corresponding energy. And if you want to know the unknown state of psi1, and you want to know the new energy epsilon, but when the light is illuminated, not the original Hamiltonian, but also the additional Hamiltonian due to the light irradiation is considered. So this one is. So there's some mathematical procedure, but you could, if you know the original state and energy, you can calculate the perturbation of energy and from the theory, and which is epsilon 0 plus blah psi 0 and h I and C. This is the first perturbation, and other energy level, other stage, you could calculate by using this perturbation theory. Okay. And the last topic you have to know to understand the band structure is statistical distribution function. And this one also have been already kind of studied, but let's review what it means again. So in a thermal equilibrium, the probability of a state with energy epsilon is proportional to the Boltzmann factor, which means that in a state of the thermal equilibrium, the particles or molecules, whatever it is, it's going to exchange the energy with a level of similar level as thermal energy, which is K by T. In this case, the probability of the state is always proportional to the minus A, B, T over epsilon. So as this exponential factor is a ratio between the energy of the state to the thermal energy. And this is it. And in case of particles like electrons, which is one of the Fermi particles, and this distribution is given by the Fermi-Dirac statistics, and this equation is equal to exponential epsilon minus mu kBT plus 1 over 1. Okay, so for a chemistry student, maybe you can more comfortable by saying this mu is a chemical potential. but in a physics student, it's Fermi, it's sort of Fermi level. So centered at the Fermi level, this function, so this function means the ratio of the electrons staying at the energy level of epsilon. So at each epsilon position, you can know how much how large the ratio is the electron occupies a state. And this function shows like this mostly, and this. So initially, for the smaller energy compared with mu, it's almost close to 1. So meaning that most likely less than mu, most of the state is occupied by electrons. And this gradually change, not gradually actually, it suddenly changed at around mu position. And once the energy is larger than mu, it's approaching to 0. So this is a function of the distribution function of electrons.